Okay. Um, Hello everyone. I had some issues setting up my stream using Streamlabs, but yeah, we would have to make this work. So this is the finals review for digital systems. This review covers both sessions, that is for Professor Nikubin and Professor Zhao. Okay. So, yeah, these are the topics that we will be going over today. So, multi-level circuits, combinational circuit design, decoders, multiplexers. Um, we wouldn't be covering demuxes today, but just decoders, multiplexers, and your logic functions, ROM, PLA, and microprocessors, and so on. Okay, so Um, first of all, for multi-level circuits, well, we have certain categories. And so, okay. Yes, so for multi-level circuits, we have certain categories. So I'm just going to put them on here. We have the and or circuits. We have or and. Okay. And then we have the, I would say, rather unpopular or and or circuit. Okay. And then this one as well. And this one as well. So how do these circuits look like? So the first being the and or, those class of circuits, they basically encompass minterms. So for example, let's say you have f equals some function, right? And let's say f is a function of a, b, and c, right? And also these class of circuits, they also include NOT gates, that is inverters. They're usually at the I would say the leftmost part of the design, the schematic. So let's say you have a bar, B bar, and C bar, yes, and then A. Let's say we have okay, A bar C. Probably simplifies, and then B C as well. Okay, I think that's just assumably this function can simplify to something simpler, but that's not the focus of this exercise. So if we were to draw f, we would have something of the like. So let's say we have our inputs, right? So A, okay, and C as well. And then we can just add inverters. So, okay, and then in this case, we're going to need 1, 2, so you can see we have AND gates here, so we're going to need a total of 4 AND gates. So I'm just going to set those up here. So largely, this topic is relatively intuitive. So relatively intuitive. So we have A bar, B bar, and let me put a C here. Okay, so that's the first term. Okay. Okay, instead of 4, let's just use, let's see here. Yeah, that should make it much more easier. So we just use 3 AND gates, and then just assume that we're allowed to use 3 input AND gates. And so for A bar and C, you would have something like this, and like this as well. So this is the first term, the second term, and then the last term is just B and C. Like I said, this probably simplifies, but that's not the point of the exercise. Okay. And now we need an OR gate, and this should be F, and then that comes here, that comes here, and that comes here. Right? So basically this is an example of an AND OR network, right? Where we have 3, 4, 5, 6, 7 inputs and a total of 4 gates, right? So it's basically just, it has I would say, the format of minterms where you have a collection of product terms and then ORs together. But the terms do not necessarily have to be minterms. It just has that format. And so we're just only going to focus on the first two. The last one is, like I said, it's relatively unpopular. So the second one is the OR AND. Let me zoom this out. Okay. 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 So the OR AND. So for this, it's basically, like I said, this should have format for the max terms. Okay. So let's say we have okay, D bar or F. Okay, just D bar F, that works. Okay, D bar F, and then let's see here, we have E or D or F. Okay, so these two should suffice, and one more term wouldn't hurt. So we just have D or E. Okay, so in this case we are going to have 3 OR gates, right? 3 OR gates. So let's say here we have this. So first of all, let's just draw our inputs and the respective inverters. So in this case, we only have one inverted literal. So one NOT gate should suffice. Okay. Okay, so that is D, E, F, and then the last is just D or E. Okay, so remember this is D. Okay, and then this is E as well. Okay, so we have our first level, and then the last level. Okay, let's see. Yeah, the last level would just be a 3 input AND, and then we put this here, put this here as well, and then put this here, and we have F. I'll call this F1, call this F2. Okay, so that is basically multi-level circuits. That is basically it. Okay, so on to the next topic, which for our purposes would be combinational circuit design. So combinational circuit design, it essentially entails designing combinational circuits based on a specific maybe instruction or problem or whatever. So usually in the design of combinational circuits, we have there is a format that we that is usually followed, right? So just to outline some of the steps, okay, basically is to so first things first is to obtain the truth table. So if you can get the truth table, you should be able to simplify using either K-maps, Boolean Algebra. Well, K-maps is based on Boolean Algebra, but so that, and also Quine-McCluskey, if you are aware of that. And so the next step would be to simplify resultant equations. Okay? And then the last term is to so the last term would be to obtain your circuits from the simplified equations. So what we are going to do is to work out a problem involving combinational circuit design and possibly possibly work out another problem involving um, more components aside from just gates. Okay, and then we would also go over conversions from and, nor, and, or, and not gates to Nand Gates and NOR gates, because those conversions are very, very important to know. Okay, so first of all, let's go back to our problem. Where is that? So the problem is here. So we have that we are to design a dual switch control for a lawn irrigation system. They are two switches. So basically, those two switches signify your inputs. So yeah, there are two switches, one inside the house, one outside. Flipping any switch turns the irrigation system from off to on or on to off. Design a logic circuit for this switch controller using the least number of two input gates and inverters. So basically, this setup is similar to, I would say, some lighting connections that are rather prevalent at homes, where two switches control a specific light, maybe a light bulb or something. So if one of those switches is on. So basically, how this system works is that for for the lights to be on, both switches would have to be in opposite states. So if you have one off, the other on, the light will be on. And then if one is off, the other is on, and then the same thing. But if both of them are in the same state, that is, if they're both on or both off, the switch or the light or whatever device is being controlled should be turned off. Okay. So with that being said, let us follow the steps that were outlined initially and see if we can obtain a solution to this problem. Okay, so first of all, let us draw the truth table. So let's just say A is for the first switch, and B is for the second switch. And we just call L our light bulb. Okay, so you have A, B. So as stated earlier, when both switches are in the same state, our system is off. Okay, so this will be off. But then, when both switches are in opposite states, our system is on. Okay, so we have our truth table. Now let us get the results into equations. So in this case, we would get the minterms, right? So the minterms for this system would be okay. So we have A bar B plus AB bar. Now, I would say not memorize necessarily, but just remember this setup. So whenever you have this setup for any two literals, it's basically A XOR B, right? That's all there is to it. It's just A XOR B. Okay, so in that case, we have gotten our equations, we got our truth table, and now let's get the circuit. So if we were to implement this system, all we would need is just one XOR gate, which is awesome. So this was I would say a trivial example, but it embodies the rules that were previously stated on basically solving combinational design problems. So now let us consider NAND and NOR conversions. Okay, so NAND gates, they're usually represented by this symbol, right? So I would just consider two input conversions, and this is applicable to n input AND gates. As long as you have you understand the logic, you should be able to extend this. Okay, so yeah, we have the symbol. Okay, so for AND gates, or no, let's start with the NOT gate first. The NOT gate. Okay, the NOT gate. Okay. So for the NOT gate, it can be so. Before we go into this, let us recall De Morgan's law. De Morgan's law. Okay. Because this is De Morgan's law is basically the underpinning that facilitates all of these conversions. So for De Morgan's law, we have that A or B bar is equal to A bar and B bar, right? And A and B bar is equal to A bar or B bar, right? Yes. Okay, so what if we were to replace B in equation 1? Let's replace B with A, and let's see what happens, right? So if we were to replace B with A, I'll call it 1 prime. You would have that A or A bar, right, equals A bar and A bar. And now if you recall your Boolean algebra rules, a literal and a literal and the same literal is equal to the literal itself. So you have A bar. Awesome. Right? Now, this is for 1 prime. Apply that to 2 prime as well. So now you'll notice that imagine that this was a NOR gate, right? So what this shows is that with a NOR gate we can get a not functionality, an inverting functionality. And the same also applies to equation 2, which I will call 2 prime now. So I'm just going to call this NAND slash NOR conversions. Okay. So yeah, the same applies again. So A and A bar, right? Which is just A bar or A bar, which is equal to A bar, right? Awesome. So now we can draw, for not, it would be A, and then just connect it to its, to the OR gates, and this should give us A bar, right? Now, let's apply that to the AND, So we know that the AND is basically the output of a NAND gate negated, right? So all we need to do for this, so imagine you had A, B, call this AND here. Okay, so A, B, ANDed. Okay, I made a mess. Okay. All right. So this should be A and B. Okay. So this gives us A and B. Okay. And the logic behind it is something of the like. So you have so it's basically just that. Okay, and then the NOR is it's not as trivial as the AND. So all you have to notice is for the OR is that A bar and B bar, or this negated, gives us or B bar, which then is just equal to A or B, right? So all we have to do is negate, so this schematic would be something of the like, hope I'm not missing my inversion bubbles in front of the AND gates. It's very easy to obviate those, but they're very important. Okay. Yeah, and this is A or B. And yeah, this can be so basically following this the same logic, you can obtain the NOT and NOR from a NOR gate as well. Okay. Okay. So moving on to our next topic. Let's see what we have here. Decoders, multiplexers, and your logic functions. Okay. So before we go there, let us consider. So what are decoders? Right. So decoders. Let me just draw something here. Okay. So a decoder basically it takes n inputs and it yields so what it does is it basically more or less converts a binary number to a decimal number. So let's see how that works, right? So it's based on an encoding technique. So let's just observe a 2 by 4 decoder. Okay, 2 by 4 decoder. So for that, and then the conversion that I mentioned, you would see how that works. So we have, for example, 0, 1, 2, 3. So the conversion is basically mapping a set of binary inputs to their minterms, which, yeah, their minterms. Okay, so let's say we have S1 as 0, right? And then this would be D0, D1, D2, and D3. Okay. So the truth table for this for a decoder, and this is a 2 by 4 decoder. So the truth table for this decoder is something of the like. So you have this. So you have D3, D2, D1, and then D0. Okay. So you have 0, 0, 1, 1, 0, 1, 1. So for 0, 0, a decoder would set all of these, what's it called? Outputs to 0 and this 1. So same applies for 0, 1, same applies for 1, 0, same applies for 1, 1. And then the rest are just zeros. Okay. So notice how each of these output terms, it's basically just mapping the inputs to its minterm. Yeah. And yeah, that is how a decoder works. And basically the inner representation of a decoder is essentially like I said, the minterms. So you could draw the minterms based on the and or um, multi-level circuits formats, which we just went over a few minutes ago. Okay, so let's work out a problem, a design problem using decoders. Okay, so let us see what we have here. Okay, so we're to use the fewest number of 2 by 4 decoders and gates to implement a 3-bit incrementer. No, sorry, to implement a 3-bit incrementer. Okay, so basically we're going to follow the same steps that I talked about before, where if you are, okay, give me 1 second. Yes. So we're going to follow the same format like before, where if you're given a problem, especially a combinational problem, and you're to design a solution, you follow the 3 steps that I mentioned earlier. So first step, let us get the truth table. So for this, we are dealing with a 3-bit incrementer. So we're going to need 3 inputs. 3 inputs. A, B, and C. Okay. And now, since it is an incrementer, at most we are going to have our outputs would comprise 4 bits at most. That is for the case where you have 1, 1, 1. If you add 1 to that, you get 8. 8 must be represented in 4 bits. And this is unsigned. So we're not dealing with 2's complement or whatever just yet. Okay? We're not dealing with those just yet. Okay. So we have this set up here, and then I'll just add the inputs. Okay, I ran out of space. Okay. Okay. And now, since we're dealing with an incrementer, basically each output here is basically just the next set of inputs, if that makes any sense. 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and then 1, 0, 0, 0. And now, since we're dealing with decoders here, we do not necessarily have to find or get the resultant equations for each output. But what we can notice very, very quickly is that the output F0, right, it's equal to C bar, right? F0 is equal to C bar. Well, let's actually prove that by simplifying using a K-map. Yeah, so in most cases, it might not be possible to simplify with a K-map, right? So if if your inputs are more than 4, well, it's not that it's not possible, but it's too complicated. You just have to use Quantum-Minkowski. Okay, so you have 0, 0, 1. Okay, so we have for 0, 0, 0, you have 1. 0, you have 1. 1, 0, 0, you have 1. 1, 0, 0, you have 1, and then 1, 1, 0, yes, you have 1 as well. Okay, my mistake. I think I might have missed something here. Okay, am I drawing the wrong output? Oh my, okay, sorry. That tripped me. So 1, 0, 1, 1. Okay. So we wipe these and we put them here. So we don't even need to add the zeros here. So this just go away like this. Okay. So it simplifies to okay. I think I made the mistake again. So yes, this simplifies to C bar. Okay, that took way too long to simplify. Okay, so the rest are, so we can see, like I said, we do not have to simplify using K-maps for this. All we can do is just make the decoders do the work for us. Okay, but now notice that we have 8 inputs, right? But we're to use only 2x4 decoders and gates. Okay, I just lost power. Oh, and it came back. Okay. So let us continue. So we have that we need a 3 by 8 decoder, but we can only use 2 by 4 decoders. Okay. Oh, I think I lost internet due to the rain. Hmm. Okay, that is okay. Let's just wait for that to come back and let's just continue. Okay, but we can only use 2 by 4 decoders. So what we can quickly do here is to compose 3 by 8 decoder using only 2 by 4 decoders. Still no internet. Okay. Okay, so how can we do that? Well, first of all, most definitely we're going to need two by 4 decoders. And now but we but our decoders also have the capability of an enable. Okay? So the way the enable works is that if the input of the enable is 0, all of the outputs would be 0. Otherwise, the outputs would be 1. Or, no, sorry, the outputs would function, the decoder would function normally. Okay? So, for that to work for us, what we have to do, still out of internet. So let's say we have B and C here, B and C here, and then we just have these outputs here. We can quickly notice that the first 4 inputs here, the first 4 inputs, B and C, B and C are periodic. So for the first 4, you have the same sets of inputs, or the same sets or class of inputs. That is 0, 0, 0, 1, 1, 0, 1, 1. It repeats, right? But A stays at 0 and then it changes to 1 in the next set. So what does that tell us? It tells us that A can stand as our enable inputs, right? So if A is 0, the AND gate changes, it inverts A to 1, and then the first decoder works as normal. But the second decoder, outputs only 0. Okay? So we have successfully concocted 3 by 8 decoders using only 2 by 4 decoders. Okay? So this first wire is M0, this is M1, M2, 3, 4, 5, and 7. Okay, so now all we have to do is basically just connect our outputs from the decoder to OR gates, right? So we're gonna need we're gonna need 2 OR gates, 2 very big OR gates. Okay. But I remember that F0 was just C bar. So you're just going to have this here for F0. Okay. And then notice again that F3 is just the midterm M7, right? So all we have to do is just something like this. This is F3. Okay. And then F2 is just minterm 3, minterm 4, minterm 5, and minterm 6. Okay, 3, 4, 5, 6. Alright, so what do we do? And this is F2. Okay. While F1 is minterm 5, minterm 6, minterm 1, and minterm 2. 1, 2, 5, 6. Okay. So midterm 1. Okay, it's raining heavily at my location. That's why I lost internet. And internet is back. Okay. Now let's continue. Hopefully I might get some. Okay. Okay. So we're done with the problem. Very good. Okay, let's move on to muxes. Okay. So multiplexers. What are multiplexers? I need to add a new page here. Move this right down. Okay, this was for decoders. So, multiplexers. Give me 1 second here. Okay, so multiplexers are usually represented by this symbol. Okay. And so you have inputs, you have select lines. So what I'm going to do is to generalize this setup. Okay. And then you have some select lines as well, and then you have your output F, right? So here you're going to have 2 to the n inputs, and here you're going to have n select lines, right? And then you label it to n to the 1 if I'm not mistaken. Yes, that should be it. Okay, so now what does this device do? What does this component do? So what it does is that, so first of all, let's just consider a 4x1 mux, right? A 4x1 mux. So you have 1, 2, 3, 4, right? And give me 1 second. We'll call this D0, D1. Okay. Okay. D2, D3. Okay. And then for select lines, we're just going to have S1, S0, and F. Okay. So what is the truth table for this? So we have something of the like. So if this is 0, it passes D0. If this is 1, it passes D1. If this is 2, passes D2. And this is 3, I'm stating them in their decimal representation. Passes D3. Okay. So that is awesome. But the good thing about muxes is that they are universal components as well. So universal components are like the AND, or not the AND, the NAND and the NOR. So basically, a universal component is a component that can that you can derive and no or and nots from. So how can we derive and or and nots from muxes? So we're going to do that right now, and also work out a mux problem. Give me 1 second. Let me pull that problem up. I think I have it here. Yeah, I'm just going to copy that question, and we will work it out again. Just give me 1 second. Just add a page here. Okay, majority function. That's what it's called. Okay, so let's see. I'm going to call this mux conversions. Okay, mux conversions. So let's start with the not, right? And we're going to, I'm going to call it 2 by 1 mux conversions, because yeah, that's what we're going to be dealing with. Okay, so for the 2 by 1 mux, you only need one select line, remember? So basically, if you have, let's say, b by 1 mux, right? To derive the select line, it's basically just log to the base 2 of b. That gives you the number of select lines. Okay, so in this case, you have this setup here. Okay, and now how? So just basically the equations for the equation for a 2 by 1 mux is something of the like. So let's just consider a general case first of all before we get ahead of ourselves. So the equation here is f is equal to a bar b or a c. Notice how if a is 0, you get b, right? If a is 1, you get c. Awesome. So now, with that being said, let us get the not conversion for 2 by 1 mux. Okay. So with this setup, we have that f equals a bar times 1 or a and 0, right? Which is basically just a bar. So I have a habit of writing the negation as apostrophes, but I should not do that. It should be bars. So bear with me if I mix them up. Okay. Yeah, let's move on. Let's move on. So for the and is, let me see. Okay, no, it's not as tricky as the or. It's the or that's actually tricky. Okay, so the and. So let's say we have this setup here, right? Okay, so this is equivalent to saying f is equal to a bar and 0 or a and b, right? This is just 0, and then you just have a and b. Nice. Okay, so now what about or, the or gates? So I did say that was a bit tricky, but it's doable. It's most definitely doable. Okay, so let's see what we have here. Wow. So notice how between the and the or is basically just flipping this bit from 0 to 1. That is pretty much it. So what do we have? We have that A bar or AB. But I thought I thought you said, or I'm sorry, I thought I said I was gonna give you the OR gates, right? Well, let's just do a little bit of Boolean algebra here. Oh, like I said, again, I am yeah, it shouldn't be apostrophes, bars. So if you apply the OR distributive property, you would have, okay, I think I mixed that up. Give me 1 second to rectify this. Okay, so this should be this. Okay, so we take this off, and then we have this, right? So the point still holds. Or distributive property, and you have something of the like, right? Okay, so we know that this is always 1. So you have 1 and A or B. Anything and 1 is that literal itself, so you have A or B. Nice, right? So definitely you do not have to memorize this. You can always derive it yourself. Okay. So let's go back to the problem. Alrighty. We have the majority function. So the majority function is equal to 1 when 2 or 3 of its arguments variable equal 1, right? And so on and so forth. Okay, let us see what can be done here. Give me 1 second. Okay. Okay, so for this, what we're going to do is apply the same set of rules as before. So first of all, truth table. We have 3 inputs and just 1 output. So it's equal to 1 when 2 or 3 of its argument equal 1. Okay, so x, y, z. So if there's anything that you gain from this class, it should be this combinational circuits design, right? The ability to get a problem, a word problem, to be specific, and yeah, just getting your circuit from said word problem. Okay, not to get philosophical, let us continue back to our problem. I'm very sorry, my throat is a bit dry, so bear with me. Okay, let me just zoom out here so everything is clear. Okay, so same process, all of our inputs. Okay, and now it says that the majority function is equal to 1 when 2 or 3 of its arguments equal 1. Okay, so this is 0, most definitely 0 as well. This is 0 as well. This is 1. This is 0. Yeah, 1, 1, 1. Awesome. So now let us write out the minterms. Okay. First of all, in fact, let's just draw the K-map and simplify directly instead of writing out the minterms. Okay. Hopefully it simplifies to some nice function or something. So 0, 1, 0, 0, 0, 1, 1, 1, and 1, 0. Okay. Okay, so we have that 0, 1, 1, it's a 1. Basically just look for the 2 or greater than in ones. Yeah, so that's about 4, 0, 0, 0. So now we can, like this, simplify like this, and then simplify like this as well. So everything is just pivoting on this 111 term. Ha. Okay. So we have that f equals, yeah, yz. Okay. Or x z, or let's see what we have here. So we have xz. Interesting. Let me just verify something very quickly. Yep, I said it. I missed something. 101. So we have 101. Okay, yeah, 101. That is correct. 110, 111, then 011. Okay. Let us see how we can get this to work with a mux. Give me 1 second. Okay. So remember that we're trying to implement this function using just one 2x1 mux, right? So having it in this simplified form does not necessarily help. It doesn't help because remember, to use a 2x1 mux, you need to have it in such a format. Let me show you something of the like. Something like this. X, I don't know, C, whatever, right? So you need to have it in such form. And there is a general concept for this, which I would explain after we work this problem. It's called Shannon's expansion. Okay, so forget about this simplification for now. Let us write each minterm. Okay, so we have x bar yz, or I'm just going to factor out this x for the remaining terms. Y bar z or yz bar, okay, or yz. Okay, so now everything inside that massive parentheses can be simplified to y or z. Okay, so if you do the Boolean algebra here, you would have to split accordingly. So you would have to do something of the like. Okay, just gonna box this over here. Factor out a y from this term. Oh no, that's just bad notation. Give me 1 second. And then if you factor out a z here, and yeah, that just gives you y or z. Okay, so we have this setup, right? Which is great because remember what I said. For you to have, or for you to implement such a function using only a 2x1 mux and gates, remember that's what the instruction said. I'm just going to zoom in. just to make it visible. So instead using only 2x1 mux and smallest number of extra gates. Okay. Oh my goodness, what did I do? I should Control Z, undo what I just did. Okay. So now we can draw our function using the mux. So now X would be the select line, right? And then this here would be an OR, this would be an, yep, okay, that does not look like an OR. Okay, yeah, something like this, right? So this is an AND, this is an OR. So you have YZ, YZ again. Okay, let us see, yep, and that should give us F. So now, the general concept, right? The general concept for this is called Shannon's expansion. Okay, so formally, Shannon's expansion is something like this. This is I. Okay, so all it is saying is that given a function of whatever number of variables, right? Just pick one of those variables, set it equal to 0, and then set it equal to 0, and then the resulting function that and the variable you picked negated, or just that same variable, set it to 1, the resulting function you get, and the literal, yeah, just the literal. Okay, let's do a quick example. And we move on to our next topic. So, okay. So now what we would do is, remember, so let's pick A, right? So you could pick any variable, any. So let's pick A, and then if we set F, that is, if we set A to 0 from F, what do we get? Well, if A is 0, then you're gonna have just BC, and then BC bar doesn't change, and then that just goes to 0. So the last term just goes to 0. Nice. And notice that you can simplify this term, right? So basically, Shannon's expansion is a tool that you can use to decompose functions into chunks in which you can apply or you can implement them using 2x1 muxes. Okay. Okay, so same applies for A. Now if we set A to 1, the first term goes to 0, and then you just have BC or BC bar, which is nice. Okay, so what we can do is to simplify. Let's just simplify this function first. I have a feeling that yeah, I picked a very nice function. So so we just basically have that's b, right? And then this one is b as well, right? So if you just factor out a b, you have a c or c bar. This is 1, so you just get b. Okay, you get b. Nice. So we have this, right? And then if you do the same process again, you just get b, right? So in this case, the function is just b. So we don't have to implement anything using any muxes. Okay? Okay. So let us go on to the next topic, which would be ROM. Okay? So just use what I did before. Give me 1 second. Yeah. Okay. Let's see notes here. So this is the setup for a ROM, right? Okay. Give me 1 second. Okay. So basically for a ROM, it's yeah, ROM is a programmable device, right? A programmable device where you have a decoder, which its outputs are called address lines or words. And then those address lines, they address a memory array. The memory array would be could be an OR plane. Yeah, an OR plane. And you have outputs. So basically, this is the innards of a ROM. A ROM is usually written in this form. So you can have multiple outputs. You can have one. It's just so basically a ROM is a hardware lookup table. So you can program it to embody your type of truth table, and yeah, basically your outputs work according to the truth table. Now, a ROM is also a universal component like the is that the yes it is it's a universal component like the 2 by 1, the NAND, and the NOR. As an exercise, you should try try implementing an or uh, an AND or a NOT gate using a ROM. So try that as an exercise. Okay, let me get a ROM problem because the best way to understand concepts is through problems. Okay, let's just take this here and let's work it out. Okay, so we are to implement the following logic circuit with two outputs, P and Q, outputs, not outputs, forget about that, P and Q using one or more of the following ROMs, 4 by 1, 4 by 2, 8 by 1, 8 by 2, and so on and so forth. So basically, we're restricted to a certain class of ROMs, right? And we're also restricted to the number of bits to use. Well, first of all, let us simplify the function that we have, and let's see what arises from there. Okay, so this out. Let me just zoom in more because the ink tends to be much more better that way. So P, and I will try to write very small as well. Well, easier said than done. Okay. So we have this. Okay. So we can notice that we can factor out a wx bar here, and then you have y plus y bar. So now for this function, you can't even use a k-map, right? It's 5 variables, so don't even try it. Do not even think about it. Okay. So we have this set up here, right? Which is nice. So all we have to do is what I'm going to do is to break these, so decompose these. So let's say f1 equals wx bar, right? And then f2 equals vz bar plus, no, it's v bar both, and then vz. So basically p equals f1 or f2, right? That would come in handy very, very soon. So all we're trying to do is to try to limit the number of bits we use, right? So the bits can be computed by just multiplying your title, the title of the ROM. So you have, for a 4x1 ROM, it's 4 bits. 4x2 is 8 bits. 8x1 is 8 bits. Yeah. 8x2, 16, and so on and so forth. Okay. So let's go on to the Q, function Q. Q equals wx bar, y bar, or w, y, z. Okay. So now, notice that if we were to implement this using a ROM directly, we're going to have to use an 8x1, right? No, not even an 8x1. It's going to be catastrophic because, okay, let's see, because yeah, we have 4 variables here. 4 variables here, which, yeah, it wouldn't be helpful at all. Okay, so what we're going to do is to rewrite this function in such a way that it works out for us in terms of the number of bits for the ROM. Okay, so how do we do that? So first of all, notice that this function, and you can try this as an exercise, this function is basically these minterms, right? These minterms. And just to quickly indicate why that's the case, I'm just going to draw the k-map and show why that is the case. Okay, so f 0 0 0 1 1 0 1 1. Okay, so we have that wx bar y bar. So let's trace it. So w1 x bar, so it's basically the third row, and then y bar, so that's basically, oh my goodness, did I make that mistake again? Shame on me. It's not 1 0, it's 1. Shame on me. What? I made it on both ends. Oh no. Tragic. Okay. wx bar, let's see, the last row, right? The last row. And yeah, y bar, so it's these two, so you have 1 1. All right, and then simplifies to the other term. right? So WYZ. So let's look for that. So W, so it's these two. YZ, let's see, it's these two. Yeah, these two. So you see, you can simplify. Okay, so you see how minterm this is 8, right? This is 9. That's 11. 1, 0, 1, 1. And this is 15. Okay, so I'm just gonna write out all of these terms. Now notice how you can factor out a W here. Factor out a W, you just have, you know, and it kind of looks like we've made this problem even more complicated. You know, you're probably asking, why, what is this? What is he doing? Why overcomplicate the problem? Well, it is necessary because notice how all of this mess of terms that we have here, they're only composed of 3 literals, x, y, and z, right? The previous case, even if you factored out a w here, you would have an x bar, y bar, or yz, right? So at best, for this, that is the term inside, you're going to have to use a 4x1 ROM here and a 4x1 ROM. Wait a second, yeah, 4x1 ROM there. And then you would also have to use another 4x1 ROM to get the OR, right? So that's a total of how much? That's a total of about 12 bits already, right? But here, you can just use an 8x1 ROM. So that saves us how many bits? 4 bits. So yeah, we did overcomplicate the problem, but you know, we saved bits. And saved money as well. Because bits are quite expensive in terms of circuit design. Okay, let me not digress. Okay, so the schematic for this circuit would be as follows. Let me draw it right here. So you have this ROM, and then this ROM. This one receives V, this one receives Z. This one receives W, this one receives X, right? And then you have F1, F2. And I'm going to descriptively draw the ROM so that it's much easier to see how it's programmed. Yeah, draw how it's programmed, right? So basically, we're programming the ROM such that the 2 inputs are 0, send out 0. And for any other sets of inputs, send out 1. Okay. So now, for this, we have just WX, right? So for WX, basically everything would be 0 except the third minterm. Okay. And then for this one, what do we have? We have, okay, so this one should be a 1. And then this one should be a 1 as well, if I'm not mistaken, yes. And then 0, 0. Alright. So now you can quickly count the number of bits we have. So right about now we have about 12 bits, right? 12 bits. Nice. So let's get the Q function. So first of all, I'm just going to draw one here because that's going to be for the AND, right? Because remember, we're ANDing this mess of terms with W. Okay. And then here we're just going to have an 8x1 ROM, program it X, Y, Z. So we're going to have how many address lines? Or sorry, how many? Yeah, address lines. So that should be 8. 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the first one should be a 1, and then you can do the rest. 1, 1, 0, which is about here. And then 1, 1, 1 as well. And then 0, 1, 1, yes, which is 3 if I'm not mistaken. Hope I have done this correctly. Yes, I think that is the case. Yeah, and so you send this one here as well. Remember, this was an AND, right? So it's just the same. Okay, yeah, so this was an OR. This is an AND. So you just program the ROM to, you know, give you an AND. And this is Q. And yeah, that's how you implement that circuit using, the stipulated class of ROMs. Okay, let's move on to the next topic, programmable logic arrays. Okay, so programmable logic arrays, they have the following the following format. So you have n input lines, right? And then you have an AND array, an OR array, and m outputs lines as well. So the inputs and the outputs, they are not necessarily related. So it's not like the decoder, and this applies to the ROM as well. It's not like the decoder and the mux where you have some exponential relationship or logarithmic relationship or whatever. In this case, they're not necessarily related. So yeah, okay, yeah. So basically for this, you can see how this AND plane programs the kind of terms that we want, right? And then the OR plane I would say it combines those terms and it yields your output. So it's kind of like the programmable logic array. If you can recall, it basically has a bearing to the AND or multi-level circuits, right? But this is just programmable. So the dots that you see indicate connections, right? So you have like this for F0, right? So F0 equals B bar, C bar, or B bar, and or B. I know this simplifies, but just forget about that for now. Okay, so you have this right here. So this is like I would say the quasi truth table for a programmable logic array. Okay. Yeah, so you have your inputs, you have them set up like that. Give me 1 second. Yeah, so you have your inputs, and C is not included for this term. That's why it's represented as a dash. The same applies to this is for C. This is for this one, right? And then the same, yeah, so you have B and C as well, and then B bar and B. And yes, so this is basically it for programmable logic arrays. I would say just recall your structure and remember that you have an AND array, an OR array that is programmable. And remember this quasi-truth table as well. Okay, so now let us move on. Before we work on computer architecture, let us just do a quick review on two's complement. Okay, two's complement and binary arithmetic, specifically division. That's division arithmetic. Okay, floating point arithmetic. Give me 1 second. So, what is the 2's complement of a number? Well, 2's complement is basically computed as follows. So imagine you have some binary number, b, right? It's 1110. Okay. Now, in the world of 2's complement, the numbers or string of bits that you'd be dealing with, um, they're signed. So they're not unsigned. They're assigned. So signed, what does signed mean? It basically means that usually this is represented by the first bit. So if the first bit is a 1, it's a negative number. If the first bit is a 0, it's a positive number. So in that case, if you have 4 bits, only 3 bits is representing actual information. The other, 1 bit is just a signed bit. So in that case, that's why, and I'm sure most of you have seen this before, integers in computers, if I'm not mistaken, yes, it's 2 to the 31. So it's negative 2 to the 31, and then 2 to the 31 minus 1. Okay. All right, so it's within this interval, integers for computers, right? So basically, right, you see that for 4 bits, the maximum positive number you can have is this, which is what? So that's 2 to the 4 minus 1 minus 1, right? Anything more than that, and you have negative number. You have a negative number, okay? While for a negative number, you can have, this and so on and so forth. So basically, yeah, that's why we have, so basically if you have n bits, let's say n bits, give me 1 second. Let's say a number x is going to be within the range this. Okay. Okay. So let's just quickly work out a 2's complement problem, and I would also show how to detect overflow, or basically just talk about the concepts of overflow and underflow. So overflow and underflow, they only work when let's say you're working with a specific set of bits. Okay. So let's see here. So let's say we have, first of all, how is 2's complement computed? So let's say you have a binary number, and we're dealing in the 4-bit world, right? So let's say you have a binary number, I don't know, 1010, yeah? Okay. No, sorry, my bad. My bad. Caught it, sir. Okay. So to get the 2's complement, all we have to do, no. To get the 2's complement, so the resultant value becomes negative b, and then you just have 0, 0, 1, 0 bar, and then plus 1. Okay. which becomes 1, 1, 0, 1 plus 1, which then is equal to 1, 1, 1, 0. So that is it for 2's complement. It's that simple. Okay, let's add some numbers and just so basically the importance of 2's complement comes when you're performing subtraction of binary numbers, right? So let's say, for example, you have a binary number. Let's say you want to subtract 5 minus 3, right? So we know that 5 in binary, and that's, remember, we're dealing in the 4-bit world. 4-bit world. Okay. So 5 is, if I'm not mistaken, yeah. And then 3, right? So basically, let's just compute the 2's complement for 3 first. So we know 3 is this, right? And then the 2's complements would be 0, 0, 1, 1 bar plus 1, which is 1, 1, 0, so it will be 1, 1, 0, 1. Okay? 1, 1, 0, 1. So now we add, because remember, you have 5 plus negative 3. You know, we don't do 5 minus negative 3. In fact, that defeats the purpose because we do not want to, subtract using the normal subtraction method. We want to add because it's much easier. Okay, so you do 1, 1, okay, normal binary addition, nothing special here. But now notice that we have 5 bits. And you might want to ask, oh, is that an overflow? No, it is not. Right? So you disregard this carry. And lo and behold, we have 2 as our answer. Well, 5 minus 3 equals 2. So basically, that's just that's the method. That's 2's complement. Just something to add. Let's see. Yeah, so if you're, performing subtraction, or better yet, if you're, okay, let me give some tips. So if you're performing an addition and a subtraction, what am I saying? So, sorry, if you're adding a positive and a negative number, you will never get overflow. And you can prove that yourself. So it's basically saying if you're at extreme ends, let's say for example you're at the cusp of the interval, right? If you add 1, you're going back into the interval. You're not going out of the interval. Okay. And then let's say you're in the cusp of the positive part of the interval. If you subtract 1, you're going back into the interval, you're not going out of the interval. So if that makes sense. And then whatever combination in between, you're only staying within that interval. So adding a positive and a negative cannot overflow. Let me just write these down. Second, adding 2 positives can most definitely overflow. Yep. So the same, you can apply the same logic, right? So let's say you're at the cusp of the interval. If you add 1, definitely you're already you're out of the interval. So so basically, yeah, just if you think about it, it's intuitive. Adding 2 positives, yeah, there is a possibility. And the same applies to negatives as well. So adding 2 negatives, there is a possibility. It doesn't happen every time, but there is a possibility of it overflowing. Okay. Nice. So now, how do you detect overflow? Well, yeah, there is a very simple way, right? So if the carry into the most significant bit is not equal to the carry that you disregard, sorry, if it's not equal, then there is overflow. Let me write that down. So overflow, underflow, yeah, basically the same thing. No, well, overflow is positive and underflow is negative. Okay, give me 1 second here. Okay, let's try an example. Remember, 4-bit world. So let's say we have 7, right? Which is this in 4 bits. And 5, which is what? So if we add these two, we get 12. But let's see what happens. Oh, yes, let's see what happens. Okay, this is not a particularly good example. Give me 1 second. Okay. No, it kind of worked. Okay, let's just do this instead. Okay, so you have so now notice that there is actually an overflow. Yes, so notice that e- 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 yeah, so notice that there is okay, going to yes, we do get 12, but remember, this is for the 4-bit world. So basically, we kind of get garbage here, right? So basically, what we're saying is negative. So if we were to convert this back to that is using 2's complement, convert it back to a positive number, because remember, the first bit is a sign bit, right? Convert it back. You're gonna have let's see here. So 0, 0, 1, 1 plus 1. That gives you what? If I'm not mistaken, that gives you 0, 1, 0, 0. Right? Which doesn't make any sense. We should be getting 12. Well, that's basic. So this example was to illustrate that this overflow detector only works So like I said, there are two, if I said this before, I'm going to say it again. There are two methods. This only works when when one of them is a negative number. When yeah, one number is negative, if I'm not mistaken, yes. Okay, hold on a second. Actually, it actually works for both. So notice how, so remember it says the disregarded carry, right? So in this case, our disregarded carry is 0, right? And the carry into the most significant bits is 1. So 1 is not most definitely not equal to 0. And yeah, we do have overflow. But, and also something to add, whenever you have overflow, um, yeah, whatever the value, the resultant value that you get, give me one second. Yeah, the resultant value that you get, yeah, it's not representative of your answer. It's usually not representative of your answer. Okay, so the other quick method to quickly know, and they're kind of similar, is that if, so there is overflow. If sign bits are 0 and sum is 1, and vice versa. Okay, so yeah, remember, and then you might think, oh, what if the sign bits are 0 and 1? Oh, remember what I said earlier? Adding a positive and negative cannot overflow. Okay. Okay. So if sign bits are 0 and sum is 1, or if sign bits are 1 and sum is 0, you, and yeah, you do have overflow. Okay, so for binary floating point arithmetic, yeah, so basically it's I would say just um, converting floating point numbers to binary. So for example, there's a relatively quick way to do this. Let's just say you have like 1054.0 point, give me one second, 0.525, yeah, oh no, 0.75, right? So a very, very quick way to do this, and there are multiple methods, but I'm only just going to focus on one. Okay. Give me one second. So what's the best way to do this is, first of all, just focus on the um, I think there is a term for this. If I'm not mistaken, it's called the Mantissa, but do not quote me on that. Okay, give me one second. Let me just verify if it's called the Mantissa or whatever it's called. Okay. Um, oh, it's called the significand and exponent. So you have the significand. So convert your significand. Oh no, that's for scientific notation. Sorry, give me one second. Yeah, significand Mantissa. But anyhow, Okay, so just disregard that. Yeah, okay, so basically convert this to, oh, I picked a very big number. Let me just reduce that. Well, not necessarily. Okay, so just convert this to binary first of all. So let's just quickly handle that. So I'm just gonna call this floating point conversion. Yes. Okay. So for 1054, that should be about, let's see, that's 10 bits, yeah. So it's 1024 plus 30. So that would be, oh my goodness, this is 256. So this is 00, 32, yeah. Yeah, that should be 1054 in binary, if I am not mistaken. Okay, let me just verify that. That was a very long number. Okay. Okay, let's see here. Okay. Okay, it is correct. Now, 0.75. So just do this. And so on and so forth. So basically, all you need to remember is that it's the same logic, right? So you know the same way you convert regular decimal numbers to binary numbers, same logic applies. Okay, so for here we know that 0.5 minus 0.75, that gives us what? So basically the same conversion. This works, right? And then 0.75 minus zero point 0.5, you have 0.25, right? So 1 over 2, or basically 2 to the negative 2, that's 0.25, right? So you have a 1. And yeah, the rest is, 0, so you don't have to include this 0. So basically, yeah, so we have something like this, right? So 1054.75 equals, okay, I'm just going to put this number here, and then 0.11. So now notice that, and most definitely you might have this question, but I guess in our computers, decimal numbers that we give, they're not as nice as this, where you can just split them up between these terms, right? Like 2 to the negative 1 to the negative 2, and so on and so forth. Well, that is very, very true. What happens in the cases where you have, like, weird numbers? Let's say, for example, you have 0.333, right? If you wanted to convert this, what we would do is to basically get it up onto a certain precision, and then we stop. Because, okay, let me just show you. Let me just show how it works. So first of all, you do like 2 to the negative 2, and then 2 to the negative, hold on, 2 to the negative 1. My bad. 2 to the negative 2, 2 to the negative 3, 2 to the negative 4. And let's say the computer that we have can only take 1, 2, 3, 4, 5 bits. Because remember, computers are finite state machines. They're not infinite. So they can only have a specific amount of bits. Okay, so we know that 0.5 is greater than 0.33, so this is 0. This is definitely 1. So 0.333 minus 0.25, you have 0. Oh my goodness. Yeah, minus that, you have 0.083. No, that is, okay. And so 1 to the 2, 2 to the negative 3, that is 0.125. So that's 0 as well, because that's greater than this, right? Than 0.083. So let's go to this right here as well. So if we go to the next one, that is, yeah, it's lesser than this, so we set this to 1 as well. So now if you subtract that, you would have that 0. This, okay, minus 0.0625. And now notice how this is getting incredibly close to 0, right? 0.083 minus 0.0625. That gives us okay. So now let's see 2 to the negative 5. That is, that is greater than this, so this would be 0. And yeah, basically, if you had a computer, let's say that worked within a 5-bit computer, right? For 0.333, this is what it would return, right? It would just return 0.01010. Yes, yeah, yeah. This is what it would return, right? And if you had a 32-bit number, it would continue the computation, so on, right? So you'll notice that this number would get incredibly close to 0. Like you have 0.00000, some number, right? So that's basically the logic behind floating point conversion. And so the last topic that we would be covering would be the processor design. And I'm just going to end my review here because I covered the pertinent material in the previous recorded review for digital systems, which you can easily locate in the Discord. If you cannot locate this video, please feel free to message me on Discord. I'm just gonna write my name here. I am a tutor. Yeah, and I'm always online, so you can easily see me in like the tutors panel. Yeah, in the Discord. So just message me and ask for the video, or better yet, if you need any clarification on the processor diagram and so on and so forth, please feel free to message me. But I would like to say that the review would end here. Have any questions, please feel free. Message me anytime. I'm usually available. Even, late at night, but okay. But yeah, have a good one, and I wish you good luck on your final and yours. I hope your semester is very good, and goodbye.